So my talk will focus, natural OEC and artificial OEC. And artificial OEC we call, this is Mn4X class. The X can be calcium, can be strontium, can be yttrium, anything else. And for here, actually, I would like some schemes. I use this slide for many, many years when I started my PhD.
Sorry.
Because almost the first year, I think my loud already.
Oh,
I don't need it. I don't need it. Yes. So when I start my PhD schemes with our lab, so he gave this slide to me. So I always use slides very much. So thanks, Jim, very much. So I don't need to talk about detail. So now we have the PS structure of the PS2. But when I in this field, we don't have the structure. We only have the cycle and the oscillation of the oxygen involving. And then we have some more information about the oxidative state of the manganese. We have the information for the proton release, electron release, but we don't have the structure. We only have the structure model based on the EPR, based on the exaf, based on the theoretical speculation. At that time, when I in this field, so I take a look at all this model. Probably there could be something we can do more. So we, at that time, 1 year later, we put calcium in the middle of the cluster. So at that time, we supposed if we propose the calcium in the middle of the cluster, connected with the 4 manganese through 3 mu oxygen and 2 carboxyl group, we can explain why naturally need calcium. But all other models, it seems very hard. So from 2001, the structure start to come out. The first way, 2000, from Junior, this the first paper, and then another from Professor Sun, then James Barber. But with 10 years, you can find out result about the study of the OEC. But here I would like to point out the 2 key steps. One is from James, and they report this structure, 4 manganese calcium seems like this. Even at that time, they didn't distinguish the ligands and know what's there. But I would say this is the first time to see, this is cobalt with 1 manganese. It's very nice. And several years later, Professor Sun, they get a breakthrough. I would say this is a breakthrough, really breakthrough. They confirm this 5 manganese, and they also find additional oxygen. More important thing, they distinguish all the ligands, including the water molecules. I was really happy when Professor Sun reported this structure, because we find in this structure the calcium indeed injected with 4 manganese through 3 mu oxygen and 2 carboxyl group. On this point, just consistent with our proposal 12 years ago. So this is also the reason. So on this point, we are right. Probably we can make it. So just during his report, Professor reported this structure. So I plan maybe we can make it in the lab. So 2 years later, Professor reported with another nice structure, strontium. In principle, they are very similar. But strontium sample is much stable than the calcium. So, but now we have still many questions. Today and yesterday, we talked about many things about the function of how to form the O bond, what function of the calcium, and the structure can be changed. And another important thing is the ligands. So what function of the surrounding ligands? But it turned out it's very hard to get clearly information. Why? Because PS2 is too big, and too many crystals have been evolved. It's very difficult to get clearly information for this mechanism. Even we have many mechanisms suggested by Sigman, by Jim, by Lubis, by Gary, and we also propose the model by ourselves. But I think yes, we still need more clearly evidence to support any of them. So what should we do? So after I finished 15 years work on natural PS2, we think we need to go to the artificial system. Maybe we can get simple model complex to make things clear. But it's turned out immediately, it's really hard. Why is it hard? Because it's hard to put calcium like this. And it's also very hard to mimic the biological environment, put water here. And its structure is unsymmetry. Another part is the redox potential of the OEC is very high, it's close to the 1 watt. It says nobody knows we can stabilize this in the solvent. Even so, there's chemistry can still make very beautiful compound. This one from Gary more than almost 20 years ago. This one from Disney groups, 4 manganese. This one, another very nice complex, 3 manganese, 2 calcium. And this one from Professor Agapi, we heard this morning. And this is, all this, as I would say, it's beautiful because nature don't have this. Especially from Agapi group, they use this big organic ligands with 6 pyridine to protect the 3 manganese so they can get this coband. So for the first time, they can form 3 manganese and 1 calcium coband. And they found that this calcium can be replaced by many ions. And they find this redox potential actually depends on the main ions. Of course, it could be also depend on the ligands, because the ligands have some effect. This morning we heard about that. Yes, what should we do? We think we need to learn from nature. This morning we heard from Holger about the structure. Without manganese, we have the structure. Actually, nature, at the beginning, actually just build the protein system. Probably leave just the place empty. So create the environment. Then follow the specific procedures called photoactivation to assemble them step by step to finally get to this structure. So we know these steps, we know this environment. Actually, this is from biochemistry many years because there's some ligand from David Brick, from Professor Gibbons. Yes, I like that paper almost, okay, let's say 1992. That's really nice paper. I read that paper and get this model from that. So this is also the reason we can predict why the calcium here. So I think maybe if we could mimic this special environment and follow the special procedures, probably we can make natural artificial OEC, like here, like this. Yes, this is our idea. We thought about this for many years, but finally we get started. Okay, so we get almost immediately we get this compound because the most difficult thing is how to put the calcium or strontium into the manganese cluster. And when we have the idea, we got to immediately get this compound. Actually, in the circle, you can see it looks very similar to the OEC. There's 4 manganese and strontium and all the types of bridge oxygen. At the same time, we can get another with calcium sample. So we can solve the problem how to insert the calcium assembly into the manganese cluster. So we are so surprised because we are so lucky because almost the next year we get this structure: 4 manganese, 1 calcium. The 4 manganese, manganese 3, 4, 3, 3, 4, 4. This structure is very clearly. And James asked me about the resolution of this structure two days ago. I asked the people, this structure data is about 0.5 in structure resolution because it's small molecule. It's no problem with all the information is very clear. So let's see the middle of the 5 meters. Actually, it's just like the structure model proposed 10 years ago. But at that time, we only get 1 crystal, but it's hard. So it's because it's very difficult. So after that, we work with magnesium. So what's going on here? Even we have some idea, but we don't know what's the intermediate state. After that, we can isolate 2 very reactive species. This one is 3 manganese and 1 calcium coband. And this one is 4 coordinated manganese 3. It is very unusual because this is really active because there's no just small acid. There's 4 coordinates. So it looks like this come together in this compound. Yes. So this coband can interact with calcium to give this structure 3 manganese or 2 calcium. So this reported by several years ago. And this is okay, our model. We can also, if without these 2, with just coband, we can get 2 coband together. Have this structure. Okay. after we understand what's going on in our system, so we can make better. So at the beginning, the yield is 0.01%. Then we can get 50% about this model complex. And this model complex very nicely reduce properties. It can carry out 4 electron reaction. The ground state, S1 state to S2 state, the redox potential is about 0.8 watt, which is just close to the OEC. So this is fingerprint EPR signal from S2, and this is from S2 state, and here is our EPR signal also from S2 state. So it is active. This is important point. This is electron surface. So when we, without water, just here, with add small amount of water, we see the catalytic current increase 100 times. So with oxidants, we can detect the oxygen immediately come out. So this picture summarizes this part. So now we can mimic the structure of the OEC 5 many times, and surrounding ligands, and also electron structure, and probably its function. Of course, there's some difference. Just like Professor he pointed out yesterday, there's 2 carboxyl group replace this rich oxygen. But I would like to point out is this artificial model complex is much smaller than PS2. So that makes things we can work very much easily than PS2 now. So, but we have a problem. This compound, the model complex, is very active. It can interact with water almost immediately. It's really unstable because this high oxide, the redox potential is very high, and so it can interact with water. The reason is the calcium can be easily released to leave the manganese there. So what should we do? We think, okay, the calcium is unstable. We have to change the calcium. So now we want to move to another chapter, X. So what about the best one? The X should be which one? So we search the periodical this table, okay? And at the beginning we said, okay, this we need probably we can go to rare earth element because from chemistry, this is very stable. This kind of and this type is very stable. So probably we can make it. And at the same time, probably we can change the electron structure because for PS2 it's always difficult to demonstrate which state. If we with the rare earth element, probably we can get another stable state. For example, it's 0 state or it's 2 state. So we have this idea. Then, okay, after, of course, many experiments, we tried, failed many times. Here, you see the structure with yttrium. So here we replace the calcium with yttrium. Yttrium is 3+ with 3 charges on the iron. But it's surprising, it's so surprising. The basic structure just same like the calcium. So it's all the distance, all the 4 manganese just the same like the previous with calcium sample. But this model complex is much stable than the calcium. It is just there, and it can go to electrochemistry. It is active, but of course it's but we need to work more. So now okay, Jim is wake up. Now, okay, from biological system we know the strontium. Can we make strontium? Yes, we can. Here is strontium. This strontium we see, and here is our model complex 4 manganese, 1 strontium. Yes, model complex. You see all the distance very close. The oxidation state is 3344. But I would like to point out, in the crystal structure of the PS2, actually there should be some radiation reduction. This redox potential, the oxidation state is not clear, but in our model complex is very clear. At the same time, we can make this cubed, 3 manganese with 1 strontium. So that makes things much easier to be studied. So now we just heard many information about what function of this manganese. So if we compare these 2 guys, probably we can get more information about what's going on this manganese. And this 4 manganese and strontium can go really good redox chemistry. And the redox pressure is very similar, almost the same like the calcium sample, but it is very stable. Why stable? The ligand can be changed. Acetyl nitrogen can be changed to acid, and many other ligands. Interesting, it can be also get water. So with water, this is the first time for us to get water in the model complex. So this means this is very stable now. So we can really work on this model complex. Another thing is, okay, it is stable, but we still want to improve it. Because the people ask me, can you use your artificial model complex for empirical in the future? We think, okay, probably we can. So we can make supermolecules. So here, we use these units for manganese, strontium, and we can use different ligands. We can get 1D and 2D structure. An important thing is it is become much stable now. And it's still active for oxygen. You can see oxygen come out immediately. Yes, another information, okay. By using this model complex, we can work on what's going on, what's about the ligands. So luckily, we find here we have this model complex. If we introduce one additional acid, just close, so we get the crystal structure like this. Basically, the structure is almost the same, but when this ligands close to the strontium from 3.4 angstrom to 2.7 angstrom, just bound to the strontium, that makes this big difference. This is closed cobalt. The distance is 2.9 angstrom, and sometimes can be 2.7 angstrom. But now it is 3.1 angstrom. So the closed cobalt just changed to open cobalt. The interesting thing is, in the lecture, in the OEC, there is one special ligand, glutamate 189. This is free oxygen, which is far away, 3.1 angstrom away to the calcium or strontium. This just like these ligands. So probably this kind of change could take place in the lattice system as well. Okay, now we heard about, okay, that's EPS2, we can see the two EPR signal, G4 and the G2 molecular signal. And the theoretical speculations suggest this is closed cobalt to relate to the G4 signal, and this is open cobalt related to the molecular signal. Okay, this is theoretical speculation. Now we can get real experiment on that. So by using the closed configuration, so we oxidize it, we can only see this signal, G4 signal. When this is open, we see G2 molecular signal. So this could be experiment evidence to support what's going on here. Another thing, so this morning we heard about, I asked about Holger about the proton release and the electron release. Probably we can handle these things by using model complex. Here, the 4 manganese, 1 strontium, the whole cluster is, the charge is 0. There's no charge. It's one state. But when we take one electron out, so we see immediately get this signal. And it is narrow, it's 1,500 Gauss rod. But when we take the proton, okay, this is, you can see the signal. After that, we add pyridine as base to take the charge away. We can see, obviously, the amplitude increase, the signal become broad, much broader. So what's mean? This is, it looks, the charge has significant structure effect on this cluster. And for the PS2, the cycle, okay, from S1 to S2 state, the people say, okay, there's one electron can be only electron release, but it's possible to get the proton release. Our model suggest maybe it is still possible. Yes, but here I forgot to show another important data. So if this model can go further from S1 to S2, then go to S3 state. But sorry, I didn't have the data here. So this is active summary. So before theoretical, we have this nice OEC structure. So it's very hard to work on it. Now we have the model for manganese 1 calcium class. And now today I will report all this for manganese and strontium class. And we even have the for manganese yttrium class. So now we have more reference to understand what's going on here. So for the future, I would like to say, okay, probably we can use this artificial model to understand, to investigate what's going on during the water splitting. And also, of course, so we want to achieve the photo water splitting by using, especially the stable model complex. Of course, there's many things needed to be done. Okay, finally, I will ask something. Okay, I have very small group, 3 students, they are new, and also my supervisor, Professor Kwang, and there's Professor Dong, and especially I thank Professor Jie. We discussed many things, many times on OEC. Okay, thank you for your attention. Finally, I will stop this picture. I would like to enjoy this picture.
Okay, thank you. Time for some questions.
Thanks for the nice talk. I was wondering, maybe I missed it. Is the strontium and the yttrium one also catalytically active, or?
Yes.
Because I didn't see the traces.
So I was wondering, for catalytic activity, one would predict that you need a coordination site for water. And in the science paper, in the appendix, hidden in the appendix, there's this nice UV vis data suggesting that upon addition of water, you get some kind of structural change or ligand exchange.
Yes.
So do you have more insight what happens if you add some water? I guess we must presumably lose some ligands
Yes.
and forming a water coordination site. Do you have more information on that?
Yes, we do have. This is also the reason why we change to the strontium, because we find if we add with water, we can get the structure. We can get different structure. The calcium just released to get the manganese complex structure. And also, it can come together, and the become dimer. 8 manganese and 2 calcium, they come together. But it's really hard to get the stable. It's because it becomes unstable now. So this is the reason. But for the strontium, so we can solve it. So we can put water there. You can see here, this crystal structure. It is quite stable, I would say. Yeah.
Two quick questions. I was wondering, related to catalytic activity, what experiments you've done to rule out the generation of heterogeneous manganese oxide that generates dioxygen?
Okay, it's hard to rule it out, but there's one thing is, so this sample, because actually this comes from calcium sample, okay? If we see the high activity at the beginning, not after. So this is the reason, because this has become unstable. So it can destroy it. So there's no activity at all. So this is the first thing. If you can form, for example, another compound, you have to, after some times. But here, you can only see at the beginning. So this is very hard. And this one, actually, the strontium sample, it can survive for several days. We put the crystal in the solution with water, and we see the oxygen immediately come out. This is measured by the oxygen type, Clark type oxygen measurement.
So is it related to the activities? For this calcium sample, when you added water here, you show 1.0% water. You do see little drifts of the current. So in my eyes, that's not necessarily to be catalytic. So my question is, what the turnover number of this? Have you detect how much amount of oxygen you generated? So I'm thinking it might be involved from the Mn4Ca bridges in your calcium sample.
I couldn't answer this because actually we didn't work this direction. because at that time we realized the calcium sample is not good. It's not stable. It's meaningless. You work that out, so it's meaningless. But now we can really work with this by using strontium sample or yttrium sample now.
Because
Yes.
the reason
Yes,
I ask
right.
it, if you see the curve, clock electron curve, within seconds, you see sharp increase, then satellite. So might be meaning some
yes, you are
decomposition
right.
process.
It's unstable. It is unstable. Yeah, you are right. So we remove this one. So to stable catalyst.
I think we should break for lunch. Thank you very much.